范进远同学有来吗？对。哦。OK。刚刚有一位同学是比较晚来，后来呢有把考卷拿走。
哦，
对。OK。Okay, so if no, so far any question? So if no question, we go through the last three. Okay. So the question four. Question four basically is some string line definition. Some students use string function to calculate this. String line definition and the string function, then we get the same result. Okay. So I just use some very basic definition, the string line definition to talk about this problem. Okay, so the question 4, basically we have an exercise as a similar question. We just have a different function. Okay, so in the chapter 1, we give some string function definition. And this string function definition, string 9 definition later on in the chapter 2, we become to a string function. Result should be the same. String function result is same like the string 9 result. So if we use a string 9 result, it's like the slope or gradient for the velocity ratio. So if we take this inside the this relationship, we can integrate y and integrate x. We take the y in the one side and take a x in the other side, then we will get a natural log, this result. So be careful about this c, because this c is a constant for the velocity, but you integration this constant is different constant. So this constant basically that means your natural log x plus natural log y. This summation natural log should be a constant. So that means the product for the x and the y should be constant as well. So if we take the exponential c, we copy this like c2. Then we equivalent to the okay, but anyway, they are constant. They are just some kind of constant. For the string 9, x, y equivalent to some constant should be satisfy this kind of velocity relationship. Okay, so you can have a different kind of velocity relationship. Use same kind of definition of a string 9 definition. So for this case, if we take the 0, 1, then that means our this C2 should become to a 0. So if you take the string 9 for the 0, 1, they should have a velocity like the x velocity become to a 0. So that means they don't have a x direction velocity, but they have a y direction in the negative velocity. So they call it negative. So in the other side, you have a negative y. They should have a velocity go upward. If you want to look different point, okay? Then similar 1, 1, you will get a constant like 1, and 2, 1, they will give a constant like 2. So in this line, they should correspond to the positive x direction velocity like this, and negative y direction velocity like this. Okay, so they will satisfy our definition for this one. Okay, so similar, if we use this velocity relationship function of x, y, we will get the strain rate like 0, and normal strain like this and this. So that means in the x direction they are expansion, in the y direction they are compression, but they don't have a rotation and they didn't change. So if you have a square, they will become longer in the x direction. Okay, so that's basically for the question 4. And then the question 5 is quite Similar for the kinematic definition as well. Okay, so this question is also in kinematics. In the kinematics, we like to see the acceleration. So acceleration is like the velocity differential, but it's a Lagrange differential, particle differential. So from this Lagrange differential, if we transfer to the Euler coordinate in the space and the time, then we will get this relationship. This is we mentioned in the very early of the class, Lagrange relationship and the Euler relationship. And all the equations should be true in the Lagrange coordinate only. Then you can see from here, velocity is a vector. So basically, some students maybe try to use the index notation or use symbolic notation. Either way is fine, as long as you can get the right answer, okay? So, for example, like this is a symbolic notation. Then, of course, we can use this to write down the index notation, like this x represent 1 and the y represent 2. This should be the index notation. But the easy way is like we write down the scalar form. For example, like this index I equivalent to 1 become to the x, and I equivalent to will become to the y. Then I just write down every term. This is the most simple and the most fundamental way. So from here, you can see acceleration in x direction. Of course, they only relate to the x direction velocity. So here, this relate to the x. But the convection term, this will relate to the x direction velocity and the y direction velocity. Okay, so you substitute into here, then you will get this result. Similar y direction, that you will get that result. Okay, so I find many students they can write down the symbolic form, but they cannot write down the scalar form. So that means this whole procedure, something maybe you are not confused. Okay, so this is I try to give this question because in the particle question, if we have a certain of a case, from the definition, this symbolic notation, or we can simplify or make a like the scalar form, like an index notation. But in the final, what kind of result you get? This is the final result. The scalar form usually is the final result you get. Okay? So the last question, I also try to give you the reality and the theoretical. I think in your undergraduate you use the ideal gas equation, but does ideal gas equation always fit reality gas equation? It's not, right? Depending on different conditions, especially in a critical condition. They are near the critical point. The ideal equation and the real gas equation behavior are quite different. So this is like the ideal wife and the reality wife. They are different, especially in a critical condition. Their behavior will be quite significant difference. Okay, so here I also like you to demonstrate the ideal thermal expansion coefficient. For example, this is the ideal thermal expansion coefficient. They should be the invert of Kelvin scale temperature, because your ideal gas equation basically is use the Kelvin scale, use a degree K. Then if you put your case in the 27 degrees C or 300 K, then you look at the table of NH3, like the exam paper. Basically, this is the original definition for the thermal expansion. So for that case, they are in the 1 atmosphere in the constant pressure. Then how you use this to represent this density? So you can use a 300 K, because 1 degree C or 1 degree K, this temperature doesn't change too much. But if you have 100 degrees C, you still use a 300 K to represent this density. Then there we have a quite significant difference, because you can see their change maybe is like 10% to 15% around. Okay, so if you want to do a detail, you can take the average for this. For this 1 degree C difference, you can get the average average density. And you can see this average density is quite similar to the 300 degree K. And also, this is differential definition. In the differential definition, basically like our shear stress, we have the distance, we have a velocity difference. Usually we will take that to replace this value. So similar for this, we have a temperature difference, we have a density difference. Then we will take a temperature difference. Like this case is a 1 degree C, we take 1. And also we take the density difference from the 301 degree to 300. And here I like to mention this one is like this value minus this value. So similar like this. The reason is if you invert, you will get a negative sign. So similar like this gradient, they will get a negative sign as well. So you should see your axis is from the, usually axis is from the small to large, So usually the gradient definition will be like this. You from the large value minus small value, this. The reason is this value is less than this value. So you will get a negative sign. That's why I like to mention, because some kind of slope is positive slope, some is negative slope. As long as your value get higher, for this case, as long as your temperature get higher, your density get less, so you will get a negative sign. Okay? So basically, this is a particle case. If you want to replace this differential term, how you use a particle result or particle measurement to replace this theoretical part. And of course, the value is not always the same. They have some kind of variation. This is quite reasonable idea and reality. Usually, we have some kind of a variation. Like my idea, you guys average score should be like 80, but reality is like 50. So I think I should put more effort to give you some kind of idea, and but I think you can see today we talk about the 6 questions, take 3 hours. Okay, but basically I think this basic idea, I think I already talked in the previous lecture. Okay. But like this kind of particle, I think many students didn't answer the second question. This particle, because as long as you know the so if you look shear stress, their definition, we use like this way, okay? And if we use other definitions, thermal expansion and some kind of, for example, like the Fourier transformation, that's kind of heat flow rate, they always have this kind of differential equation, and they always have a reality part. I just try to give you some idea how to relate particle and the theoretical, but we cannot talk all the case. You probably need to think about how to relate them together. Okay? Okay? So you can see quite similar, right? And in the future, I hope you can not just use this, it's like a theoretical part. Because the theoretical part, usually it's like you can solve the question in the exam, you can solve the question in the homework. But in the research, usually you have some kind of particle problem. Then how you use this basic knowledge to the research problem or particle problem. I think this is a graduate school purpose. Okay? Okay, so we probably have a couple minutes left, 5 minutes. Not much. So we don't have too much time to go further. So about exam, any questions? This is first. The second part, last time where we go. Because I was sick 1 week. Have we finished the boundary layer part? We already talked about boundary layer part in the last lecture. Okay. Because today, for example, like this exam, we also have one boundary condition, like the shear stress. This is one of the boundary conditions. They are fixed boundary condition and the moving boundary condition. And some boundary condition may be more complicated. For example, like the sea surface or the lake surface, they have a free boundary condition. So in this kind of free boundary condition, what kind of condition that need to satisfy? Usually the pressure. For example, like the sea surface, why they maintain this kind of a shape? Because they, on the surface they should have atmosphere pressure. If the pressure less than the atmosphere pressure, this kind of air they should penetrate into the water level. So in the other side, if the water inside has a very huge pressure, for example, if you push up, this kind of surface will change as well. So basically, that's kind of a boundary condition is balanced with a normal stress pressure. Then that will be different from the shear stress boundary condition in this kind of interface level. Okay. So maybe next time we will start from after the boundary condition, we talk about the basic Gaussian equation. Okay. But I really hope you guys can review this kind of problem, because this problem basically before the midterm, especially I was sick 1 more week, so we talk less. Before the midterm, we supposedly it's some kind like a review the undergraduate part. Some maybe you are not quite familiar, and some maybe it's not taught like so mathematically. In your undergraduate, mostly you should talk about the control balance method and the differential method and the dimensionless analysis. Basically, these courses we focus on the differential analysis. Because of control balance, we suppose undergraduate students should understand. If you go to any engineer company or you are go any exam, national exam, graduate school exam, they will always test this kind of control balance problem. So that problem usually we will see undergraduate students should have enough ability. So that's like we talk about some case, we don't use too much integration, we don't use too much differential equation. Usually that's we regard as the undergraduate problem. But in the graduate school, we will start from this kind of a basic differential, integration, and what does it mean. So that's why we take so much time to talk about the vector calculus. Because later on you will see many Gaussian equations. They have a different kind of direction. They come out should be a vector, or come out should be the scalar, or come out should be the tensor. So we cannot talk individual equation like that way. Okay? So that's why we give you some kind of a fundamental idea. So if you look, supposedly after this mathematical language, you should able to look most 80% or 90% of a research paper talk about a Gaussian equation without the problem. Okay? Okay, so if no question, we just finish here. Okay.